Hashvi. Hello, Marina. Hello, Dr. Stratham's Bush. What a great day to be in class today.
My name is Adam, or Dr. Bush, and this is BME 311.
I'm very excited to see your presentation. I'm pulling up on screen now.
We hypothesize that when exposed to significantly colder temperatures, vasoconstriction will occur, increasing vascular resistance and decreasing arterial compliance. To test our hypothesis, we utilized MATLAB to model a two-element Windkessel circuit to predict the outcome and relate it to experimental findings.
For the first part of this experiment, we used a sine wave function to model blood flow in a Windkessel model circuit with ranging compliance values. Euler's method was used to update the pressures at each heartbeat to track the pressure changes. As the compliance increased, the amplitude of the pressure wave decreased, indicating a lower pulse pressure. Next, we investigated how regurgitation affects the pulse pressure by updating our flow equation to model 10% and 30% regurgitation in the flow equation. As you can see in the graph, increasing the regurgitation percentage decreased the amplitude of the flow wave. We used Euler's method once again to find the pressures over time and saw that increasing the regurgitation fraction decreased the amplitude of the pressure wave. This is important to understand because aortic valve regurgitation is a prevalent issue, with around 5% prevalence in the world population. Its onset is typically accompanied by increased heart strain, ultimately leading to heart failure.
For part 2, to test if resistance actually increases and compliance decreases with cold exposure, we measured the blood flow and compliance of the brachial artery before and after dipping our forearms in an ice bath for 1.5 minutes. For resistance, we measured the blood flow using Doppler imaging. Because flow is equal to pressure over resistance, an increase in resistance means that flow decreases if the pressure stays constant. Thus, we confirmed our hypothesis that the resistance increases with cold exposure by measuring the decrease in flow rate. We measured compliance using ultrasound imaging and the following equation. The graph shows a clear decrease in compliance following the cold test, and we predict this is due to stiffness increase.
Vasoconstriction occurs in response to cold exposure to reduce peripheral blood flow and limit heat exchange with a colder environment, thereby conserving core body temperature. During a cold pressor test, used to evaluate autonomic and cardiovascular responses such as those seen in the mammalian dive reflex, cold stimulation activates the sympathetic nervous system. This causes a homeostatic response that constricts peripheral vessels, redistributing blood centrally to protect vital organs. This vasoconstriction reduces arterial diameter and increases vascular wall stiffness, thereby decreasing compliance and increasing total peripheral resistance. As a result, systolic blood pressure rises due to the greater force required to overcome the reduced arterial capacitance during ventricular systole. In compliant arteries, pressure is absorbed and distributed more effectively. However, with increased rigidity, the cardiovascular system experiences elevated systolic pressures, reflecting the diminished ability of arterial walls to buffer pulsatile flow.
With the Windkessel model, we can compare the cardiac circuit in our experiment directly to a normal electrical design. The current or blood flow is dependent on the changes to other components. Pressure or voltage remains constant throughout. The arterial resistance depends on cross-sectional area, and the compliance is the capacitor. We would shape this with parallel nodes between the voltage source, the compliance, and the resistor. We can use this equation to test this. The model helps us predict how pulse pressure, diastolic runoff, and vascular stiffness influence cardiovascular performance, particularly under pathophysiological conditions like aortic regurgitation or arterial stiffening.
Future research could include subjects across different age, fitness, clinical background, and ethnicity groups to assess how vascular compliance responses to cold differ across populations. Advancing the model by incorporating characteristic impedance would improve accuracy in simulating wave reflections in early systolic flow. These insights could enable real-time compliance monitoring through wearable ultrasound cuffs, enhancing at-home cardiovascular assessment. Personalized predictive models using flow and velocity data could estimate compliance or pressure trends, aiding in early detection of genetic or chronic conditions. This work is fundamental to biomedical engineering and medical education as it deepens our understanding of cardiovascular responses to physiological and pathological changes.
Oh, that must have been so cold. Oh,